This will just give you some idea of the state of the art of the field at present. But if you worry about what hey, before we move on, you're still running LZ and you're pushing down to lower cross sections. It's possible that darkness cross section per nucleon that's in this range here. If it's not there, then it's going to be very difficult to get the smaller cross sections because we'll be limited by neutrino backgrounds of the nutrients in the atmosphere, scattering, previous areas of the background. And so experiments, at the thousand ton scale, pretty probability of ways to figure this that. So you can say, dark matter still might be here. Everyone's looking for the wind, still very motivated. And that should be right around. But meanwhile, we should be thinking about other places to look for dark matter. And instead of going bigger with xenon experiments, you can also think about building experiments that go lighter with your target materials and have is where the energy threshold is lower. And so that's what I'm talking about for this today. You can imagine as the dark matter mass is going down, its velocity is set by velocities of particles going in the Milky Way, so energy happens there. But the dark matter is dropping, and then the possible kinetic energy the dark matter particle would give to one of your nuclei in your detector is dropping as well. So xenon experiments, your energy threshold from keV, and that ends up setting a limit on how low you can go with dark mass. So it gets out that the dark matter is light. You could have billions, trillions of these scattering in a second. It's quite possible. Because there's all this unexplored dark matter parameter space at low mass and high mass. So it is really large explored parameter space below 10 GeV. And over 50 years, there's been increased effort on the theoretical side to think about models that can give you dark matter particles that are sub GeV. I'll talk about this and the motivation, but there's a number of other models who dissected dark matter models, thermal relics, hidden thermal relics, asymmetric dark matter, freezing dark matter, Simpson elders. And this is sort of another hotbed of theoretical physics lately, is thinking about what model could be give you dark matter masses, particle masses in this range. Here's a nice summary you can read on the archive about a lot of these models that one can think about for that people like use the dark matter right now here in the universe. So there's a lot of work to do to search for dark matter particles in that mass range. So in the US, there was an effort that was basically sponsored by the Department of Energy in 2018. All these theoretical models were being produced. And a lot of the community was saying, well, we really should be thinking about new experiments to look below GeV. And it turns out when you think about particles that interact by electron recoil detection or nuclear recoil detection, we can also think about dark matter particles that are light enough that they have a long enough wavelength that they can scatter off many atoms in return for specific ones, like an X-ray would scatter a whole set of atoms in a crystal. And ideas for what parameter space we should be looking for, what might be possible with your new technologies, what might be possible with our term, going down to the few keV scale. In the near term, which is the experiment I'll be talking about, we hope to be able to probe some of these orange and green images in this kind of parameter space, which is really a cartoon. The dark matter can live anywhere in this parameter space. And you can also think about searching for these light dark matter particles using accelerator experiments. And it turns out that depending on the nature of the development's interaction, you might see the accelerators, you might see the direct detection experiments, or both, or neither if you're lucky. And what happens to do is exactly how the architect is. They are from separate constants in order one, much smaller. Um, the direct detection experiments, you can get very small magnetic transfers, so Q is low, and the mediator mass, if it's low, can give you a big enhancement in the scatter cross section for these direct detection experiments. Well, one thing when you think about regeneration is that you can get by with a very, very small detector, low mass detector. I mentioned that the limits on the cross section are very weak if you look for a low mass dark matter. And so it turns out that even at gram scale detectors, you can be looking in new parameter space. You might be able to run a gram scale detector in your basement. And in principle, dark matter probably be gathering all the time. And you have improved sensitivity to see very low emission events. You might be able to see some dark matter events in a very small top scale experiment. There you have a rate going as some cross section times the density of the dark matter times the number of atoms in your experiment. And this density of the dark matter is equal to one of the dark matter particle mass. So we can talk about various fluxes and something, person size experiment here with a gram scale detector in the middle. Look for dark matter models that have never been proved yet. In addition, if you're looking for a recoil signal, you can still be looking at these very low energy recoil and get some of the same advantages you have in wind searching. We have coherence over the dark matter scattering. Neutron backgrounds are much lower rate than electron recoil backgrounds, so if you have discrimination power between nuclear electron recoils, you can use that to your advantage. The lower your backgrounds overall. Those nuclear recoil backgrounds already can be small compared to gamma ray or electron X-ray backgrounds that create electron recoils. Okay. So these numbers for why we can be studying the document for the court. And these little things have to develop a consensus, and it can take a very long time. There's the community and the funding agencies that you can do these kinds of experiments. But in still after that DOE report in 2018, continued work in the snowmass exercise. In 2022, the report comes out and it says not only should we delve deep looking for implicit source or cross-section, looking for axions that's lower or something extreme. We delve in searching wide, develop new techniques to access unexplored dark matter in space in areas that we haven't looked before, and lay the groundwork to go deep on future targets. And it's also true that the detector technology is really across fields. We think about using a novel as matter effect or techniques from time physics to inspire new ways to develop new technologies to develop that. And then following that, next year, there was a P5 report in the Department of Energy, and it ended up applying both a new big dark matter experiment we produced, but also a set of small-scale direct detection experiments. So here there's the recommendation to do the G3 experiment, but there was a key recommendation to have a small project portfolio across science, and particle physics, but it should start with the construction of experiments for the dark matter derivations program by DOE hydrogen physics. So this was a major impetus to build new experiments to look for light dark matter. So that's where we're focused on, sort of sub-GeV, EV scale dark matter, referred to the TESSERACT. So the TESSERACT is this new collaboration. TESSERACT So the transition edge sensors with sub-EV resolution and cryogenic targets, which is a good snapshot of what the idea is behind the experiment. I mentioned in the Xenon experiment, you have sort of EV thresholds. Here, the TESSERACT will go to sub-EV thresholds. It's a much lower energy. And another idea that we have multiple targets, different ways that the dark matter could scatter, materials that the dark matter could scatter and look for those recoils, whether electron recoils, nuclear recoils, really developing a number of different ideas for how you could look for these light mass dark matter particles. With TESSERACT, included over 60 scientists, researchers, engineers, product managers, postdocs, and grad students who were from the US and and I'm very happy to say the University of Zurich is one of our places we're proud. I'm very happy to be here. So, ingredients you consider. One, you have to have sensors that are really, really sensitive. Sub-EV resolution. Second, you want to have this variety of targets that are all read out using this technique. And you also want to be underground. And we're going to be going underground in 2 years in the lava response compared to the model. In terms of telling more, well, it needs to go to the community along all the foundation. Well, pretty much, you have some absorbers, some crystal, like silicon, gallium, or something like that. And if you have an energy deposition in your absorber, then you create a whole bunch of photons, quantized particles found. If that photon has enough energy to break apart a Cooper pair in aluminum, and that photon comes to the aluminum around, and excited aluminum quantum particles. And then those quantum particles can migrate to a transition edge sensor. What we use is tungsten W. And this little bit of tungsten is biased and superconducting normal transition. And a little bit of energy will increase the resistance of the tungsten. It'll force current to be driven through a shunt resistor, and that current driven through a shunt resistor can be measured with a squeal. Superconducting quantum inheritance device with an amplifier. So it's the machine, we want to get as small as possible, the city E. It's smaller than the volume as the TESSERACT volume is more. And it also improves as the critical temperature or the superconductor TC gets smaller. It's very strong attendance in TC. So in practice, we're going to get TC as low as we can, but not lower than that. Let's see. Now, what's amazing is that we can result in this using this technology, all the way down to the world of 300 million. And this leads to this very striking LD or laser on the square centimeter device, and we can count every photon that hits it and know the energy of every one of those photons. So this is like a significant this experiment. 100% efficiency when you measure the photon every one of the time. So this is what really gravity is about. It's something that we want to use for these future documents. So this is where we are right now. We have to continue to reduce and improve that energy dissipation depth. One of them is sapphire, is a crystal, sapphire, and collected by TESSERACT is WIMPs. One is silicon vanadium, where you put a field on the silicon vanadium, and you collect individual electrons, and you also put photons and neutrinos, gases. Another is gallium arsenide. Gallium arsenide is a very bright simulator. maybe what, both photons and photons, gallium arsenide.